Now that we know the domains and ranges of the inverse trigonometric functions, let's recall the cancellation properties of the inverse functions in general. So previously we had discussed how f inverse of f of x is x for all x in the domain of f of x. This will be true with our inverse trigonometric functions, except we have to replace, again, the domain with the restricted domain. Essentially, all of these things that we learned in the series of videos that we discussed in inverse functions is true here as well, except whenever you have a statement that says domain of f of x, you have to replace domain with the restricted domain. Note that it doesn't make sense to replace this here with restricted domain because f inverse of x doesn't have a restricted domain. The domain that we restricted was the domain of the original function. So this second statement is also true. F of f inverse of x is x for all x in the domain of the inverse function. If you ever want to use this cancellation property and if you forget, do I need to be in the domain of f inverse or do I need to be in the restricted domain of f, just take a look at the first thing that x is being plugged into. So in this first case, x is being plugged into f, so you need to be in the restricted domain of f. Whereas in the second statement, x is being plugged into the inverse function, so x is going to have to be in the domain of the inverse function. So this is a statement in general about inverse functions. These statements that I've written here work whether your original function is a polynomial, or perhaps a rational function, or an exponential function. Let's apply these two facts. Let's label them 3 and 4. Let's apply them to our inverse trigonometric functions. And I'm actually going to start with the type of composition that looks like what I have in this fact 4 here. So we're going to say what is sine of sine inverse of x, tan of tan inverse of x, and cosine of cosine inverse of x. These, well, let's start with the first one. This is going to be equal to x, and let's look back at our fact here for all x in the domain of the inverse function. That is, sine of sine inverse of x will be x whenever this input is in the domain of the inverse function. So you have to ask yourself, well, what is the domain of the inverse function? Well, we answered that previously. The domain of the sine inverse function is minus 1, 1. So this is going to be true for all x in minus 1, comma 1. So if you do sine of sine inverse of some number between minus 1 and 1, you just copy the number here, and that's your answer. For the second one, this will be equal to x for all x in the domain of the tangent inverse function. And the domain of the tangent inverse function is all real numbers. So all x in minus infinity, comma infinity. And then finally, cosine of cosine inverse of x will be x for all x in minus 1, comma 1. Because the domain of the cosine inverse function is minus 1, comma 1. So if you ever come up to a problem that asks you to do something like, let's say sine of sine inverse of, let's say 3/4, then you can do this quite quickly just by asking, okay, is 3/4 in the domain of my inverse sine function? If it is, which it is because it's between minus 1 and 1, I'm simply going to copy 3/4 and I'll be done with the problem. However, if you do something like sine of sine inverse of 5, the answer would not be equal to 5 because 5 is not in the domain of the inverse sine function. In fact, this is undefined because 5 is not in the domain of the inverse sine function. So let's write that. So since, for this first one, -1 less than or equal to 3/4 less than or equal to 1. So I'm explicitly saying here that 3/4 is in the domain of the sine inverse function. However, this is undefined, the second one, sine of sine inverse of 5, since 5 is bigger than 1. Now, if you replaced sine with tangent, then both of these examples would work out as you would expect. More specifically, tan of tan inverse of 3/4 is equal to 3/4, but also tan of tan inverse of 5 is equal to 5 because the domain of the inverse tangent function is all real numbers. And then finally, the situation for cosine is exactly the same, or excuse me, the situation for cosine inverse is exactly the same as for sine. If you wanted to do cosine of cosine inverse of 3/4, then this would be equal to 3/4. But if you wanted to do cosine of cosine inverse of 5, then this is undefined. Now let's go back and examine the types of problems that look like what I have in fact 3. So remember, f inverse of f of x will be x for all x in the restricted domain of f of x. Again, this is a fact about all inverse functions, but let's see what it means in terms of our inverse trigonometric functions. So sine inverse of sine of x will be equal to x for all the x's that are in the restricted domain of the function that comes before it. So for all x in the restricted domain of sine of x. So the restricted domain of sine of x is minus pi over 2 to pi over 2. So this is for all x in minus pi over 2, comma, pi over 2. And let's see, I think I can write that a little bit better. What about the second fact? Well, this will be equal to x, tan inverse of tan of x, whenever x is in the restricted domain of tan x. So for all x in, and now I'm not going to put, well, I'm going to put minus pi over 2, comma, pi over 2, but with parentheses, because the restricted domain of tangent of x has parentheses on it. And then finally, this third fact says that cosine inverse of cosine of x will be x for all x in the restricted domain of cosine x, which is 0, comma, pi. So for example, sine inverse of sine of 1 would be equal to, well, you have to ask yourself, is 1 in minus pi over 2, comma, pi over 2? If it is, you can simply copy and put 1 down here. And the answer is, yes, it is. Pi over 2 is about 1.5. And so this is equal to 1 since negative pi over 2 is less than or equal to 1, less than or equal to pi over 2. In other words, since 1 is in the restricted domain of the sine x function. And if we replace sine with tangent or cosine, then we would get a true statement as well. Tan inverse of tan of 1, that's going to be 1 since minus pi over 2 is less than 1 is less than pi over 2. Again, this is just saying here that 1 is in the restricted domain of tangent of x. And then finally, cosine inverse of cosine of 1 is equal to 1 for a different reason though, since 1 is bigger than 0 but less than or equal to pi. Now I think it's worth mentioning here that for these 3 examples that we have, it would be very challenging to evaluate this by hand, if not impossible, if we did not have these cancellation properties because, well, let's take a look. Let's think about how we would evaluate sine inverse of sine of 1 if we didn't have these cancellation properties. Well, what I would do is I would say, okay, let me try to figure out what sine of 1 is. But the problem with that is that the angle 1 is not an angle that we know the trigonometric functions of. It's not one of those special angles that we know on the unit circle. And so this calculation, I honestly do not know how I would go about doing it if I did not have these cancellation properties that I have mentioned up here. If it was something like sine inverse of sine of pi over 6, well then you could evaluate this by hand without using these inverse cancellation properties by first figuring out what sine of pi over 6 is, and then figuring out what sine inverse of what sine of pi over 6 is. However, it's still much more work, right? You can simply say that this is pi over 6 because pi over 6 is between minus pi over 2 and pi over 2.